Hello sir, my name is N. Kamal. Today I am here to present my CA2 assessment on distributed training and optimization techniques in big data. Then coming to first introduction to distributing training in big data. Distributed training involves splitting data and model computation across multiple missions to handle large data sets. It significantly reduces training time and improves scalability for complex models. Understanding the core concepts is essential for optimizing performance in big data environments. The importance of distributed training. As data sets grow exponentially, single mission training becomes impractical due to memory and computational constraints. Distributing training enables handling vast amount of data efficiently. It is crucial for deploying advanced machine learning models in real-world big data applications. Then data parallelism. Data parallelism replicates the entire model on each node and process different data batches concurrently. Gradient are synchronized across nodes to update the model uniformly. This approach is widely used due to its simplicity and effectiveness in many deep learning tasks. Model parallelism explained. Model parallelism partitions a large model into smaller segments to fit into memory of individual nodes. Each node computes its segment and communicates with other to complete forward and backward passes. It is beneficial when model size exceeds memory capacity but introduces communications overhead. Communication challenges in distributed training. Synchronization of the gradients of our parameter requires efficient communication protocols. Communication overhead can negate the benefits of parallelism if not properly managed. Techniques like asynchronous updates and gradient compression help mitigate these challenges. Then optimization techniques for distributed training. Gradient averaging ensures consistent updates across nodes in data parallelism. Learning rate adjustments such as warm-up strategies improves converge stability. Advanced optimizers like Adam or LAMP are often employed for better performance. Compression and quantization. Gradient compression reduces the size of transmitted data, decreasing communication costs. Quantization techniques approximate gradients with fewer bits, maintaining the model accuracy. These models are vital for scaling distributed training to hundreds or thousands of nodes. Asynchronous and versus synchronous training. Synchronous training waits for all nodes to complete their computations before updating parameters. Asynchronous training allows nodes to update parameters independently, increasing speed. These choices dependent on the trade-off between convergence, stability, and training speed. Fault tolerance in distributed systems. Distributed systems must handle node failures without losing training process. Checkpointing periodically saves model states for recovery in case of failures. Frameworks like Apache Spark and TensorFlow provide built-in fault tolerance mechanisms. Frameworks supporting distributed mining. TensorFlow offers distributing training APIs for both data and model parallelism. PyTorch distributing package facilitates flexible multiple node training setups. Apache Spark integrates with ML library for scalable machine learning workflows. Hardware consideration. High performance GPUs and TPUs accelerate training significantly in distributed environments. Network infrastructure such as InfiniBand or high band Ethernet reduces communication bottlenecks. Memory bandwidth and storage input and output are critical factors influencing overall system performance. Then optimization algorithms in distributed context. Stochastic gradient descent (SGD) remains a foundational optimization method. Variants like Adam or LIMP adapt learning rates for better convergence in distributing the settings. Adaptive algorithms helps address issues of stable gradients and asynchronous updates. Stability challenges and solutions. Scaling up involves balancing computational load and minimizing communication overhead. Hierarchical communication strategies improves the in larger clusters. Algorithmic innovations like decentralized training reduce dependency on central parameter server. Case study: distributed training in industry. Major companies like Google and Facebook utilize distributing training for large scale models. Techniques such as parameter server architecture and all reduce are commonly employed. These implementations enable training of models with billions of parameters efficiently. Future trends and research directions. Emerging methods focuses on reducing communication through smarter compression techniques. Learning introduces privacy preserving distributing training across devices. Quantum computing and neuromorphic hardware may reduce distributed training paradigms. Best practices for implementing distributed training. Carefully choose the appropriate parallelism strategy based on model size and data characteristics. Optimize hardware configurations to minimize bottlenecks. Regularly monitor training performance and adapt strategies to improve efficiency. Challenges and limitations. High setup complexity and infrastructure cost can be barriers to deployment. Ensuring model convergence and consistency remains a significant challenge. Data privacy and security concern must be addressed in distributed environments. Then summary and takeaways. Distributed mining is essential for scaling machine learning to big data volumes. Effective optimization techniques and hardware considerations are critical for success. Ongoing research continues to push the boundaries of efficiency and scalability. Thank you.